Good morning. Welcome everyone to the third day of QTech-Budapest conference. My name is András Pályi. I'm from the Budapest University of Technology and Economics, and I'm going to chair this first plenary session of the day. We have 3 items, 2 plenary talks, and then in the end, in a few minutes, we will also hand out poster awards. So yesterday we had a poster session of the Spin Qubit session, and then we will hand out third prize, second prize, and first prize. And this is going to be the last moment of this plenary session. But first, the plenary talks. The first one is going to be given by Christian Andersen, who is an experimental physicist, an assistant professor at QTech in Delft, the Netherlands. A brief CV of Christian. So he obtained his PhD at Aarhus University in Denmark in 2016, which he followed up by joining ETH Zurich as a postdoctoral researcher before taking his current position in Delft in 2021. His research focuses on superconducting qubits and addresses the challenge of achieving the highest performing qubits through novel qubit designs. Today, Christian will tell us about superconducting qubits and hybrid qubits. Christian, thanks for coming, and looking forward to the talk.
Great, thank you, Andres. So this is a nice introduction. And as was mentioned, today I will talk about superconducting qubits and hybrid qubits. In this conference, it's one of the rare conferences that I go to where superconducting qubits is somehow in the minority. So I will represent superconducting qubits on behalf of the field, and then talk a little bit on how it relates to some of these hybrid qubits that you've also seen, for example, in Leo's talk yesterday and in the nice hybrid session yesterday. So first of all, I want to just maybe take a step back and just remind ourselves what we are actually trying to do here. And what we're trying to do is to build quantum computers. And the reason for that is that some people say they can do a great many things. So this picture here is from IQM. It's a European quantum company, builds nice quantum computers, and they say you can do healthcare and logistics and finance and materials. This is not to point at IQM, they just have very nice pictures, so I took this. But I think it's really, really important, and maybe this is a good thing to, maybe not every day, but at least, let's say, once a week, we should remind ourselves that getting to any of these applications is really, really hard. And it's also unclear if we can really get there. Maybe for some of them, we have very good ideas that how we can get there. For some of the other applications, the algorithm is unclear whether it's going to be really useful. And the path to get there, even if it would be there, is unclear, right? And this is, let's say, different than, let's say, running a marathon. If I run a marathon, if I go to the London Marathon and I run it, it's hard, but somebody made a path, and I know if I follow the path, I will get there, maybe eventually. For quantum computing, there's no path. There's some ideas of some paths, but we don't have a final path. And I think this is something that we should, I think, at least once a week remind ourselves of. And then the other thing that I think is very important when you start asking these questions about where to go, we should start with the very basic question, which is how many qubits do we really need? Because that's going to impact the decisions we make when we are trying to make our path. And we can break down these numbers in sort of two categories. First, we can look at the algorithms themselves. Typically, for most of them, if you break down the numbers, they say you need around 1,000 qubits. It's plus minus a little bit depending on the algorithm, but let's say think about Shor's algorithm. You want to prime factor a 2048-bit number, then you need probably at least 2048 qubits, plus a bit more. So let's say thousands of qubits. Then the second thing you need to do is quantum or qubits are generally very, very lossy. They make errors. We don't have 100% fidelities. Maybe we have, if you're very good, 99.9% fidelity, but that's not enough. For quantum algorithms, such as the ones I showed, hinted at before, you typically need around 1 billion operations, which means you need error rates on 10 to the minus 9. And the only credible way we can get there is quantum error correction. And typically, if you look up current schemes for quantum error correction, they will say give or take a few hundreds, you will read around 1,000 qubits per logical qubit. So you can multiply those two numbers. I should do it like this. You can multiply those two numbers, and then you get that in total we need, give or take, 1 million physical qubits. But this number here in quantum, for the quantum error correction part carries a lot of assumptions, right? It assumes what error correction code you're using. It assumes how good are your qubits. So these are made based on assumption that maybe you have 99.9% fidelity, and then you get this number. And so if you want to do better, you need to reduce this number. You need to A, make better qubits, and B, you need to make smarter choices. Because I think if I look at this number, 1 million qubits, that seems really, really hard. And I think if we could make it 100,000 or maybe even 10,000, I think we would all be much happier. So that's the goal of this talk, is to try to answer the question, how can we try to reduce this number such that we don't need that many qubits? And we do that by making better qubits, and we make smarter choices. And what do I mean by better qubits? Okay, there's many ways you can think about what is a better qubit. It could be you have higher coherence times. Maybe they're easier to operate such that you can just build many of them and they just operate themselves. Or maybe they add functionality such that it's easier to make some of these smarter choices that I mentioned. And the platform that I will focus on to try to answer this is superconducting circuits. There's many platforms that you can use. What I will focus on is superconducting circuits. So for those not so familiar with superconducting circuits, we make them basically out of electrical circuits on a chip, but because it's superconducting, it's lossless, which is of course not true because there's always some losses, but at least there's no ohmic loss, which means you can get very good coherence times in these circuits. And if you just sort of take the basic thing, you can make a circuit where you take a superconducting capacitor and you make an inductor, and then you have what we call an LC circuit. And in the quantum regime, it works as a harmonic oscillator. This is the basic building block for many things that we do. But a harmonic oscillator is not enough to build a quantum computer. You need some things that are anharmonic, some nonlinearity. And in superconducting circuits, that is the Josephson junction. Hopefully you have heard about the Josephson junction before. There's these Josephson equations that are very, very famous. If you sort of put those together and do the math, you will realize that actually the Josephson junction, even though it's sort of maybe counterintuitive, it's two metals that are on top of each other, right? Looks a little bit like a capacitor, but it's very, very much smaller. But it actually works as an inductor. And you can do that by showing the math here. So the fact that you have two Cooper pairs tunneling across this barrier means that it actually works as an inductor because of the self-inductance associated with this tunneling. Physically, it looks something like this, at least when we make them in our lab. So the Josephson junction sits sort of right here. So what we do is we deposit some aluminum, then we oxidize this aluminum, create an oxide barrier on top of it, and then we come with a different layer of aluminum. So we first put the red line, then we wait, then we put the blue line, and then we have a Josephson junction. And then we do a little bit of patching here to then connect it to the rest of our circuits, and this is how we make a Josephson junction. Now, with the Josephson junction, we have this nonlinearity to make a qubit, and the basic building block of many superconducting qubits is the transmon qubit. It's similar to the LC circuit I mentioned before, so you have a capacitor here, but now you replace the linear inductor with this nonlinear inductor, meaning the Josephson junction. We symbolize this with a X. And what that gives rise to is a potential that looks almost like a harmonic oscillator. So the harmonic oscillator is shown in this potential as a function of the phase. And the dashed line is the harmonic oscillator, and the transmon potential is this solid line, which is now a cosine, which at the bottom looks a little bit like a harmonic oscillator, but it then deviates a bit. And this a bit is enough such that we can energetically separate the ground state and the excited state from the higher excited states, and we can define a qubit in these two states. What we also often do sometimes is we, instead of just making a single junction here, we make a loop of two junctions such that we can thread a flux through this loop, and that can give a way of tuning the Josephson energy, or effective Josephson energy, I should say. The transmon qubit is relatively easy to make. Of course, easy is always depending on who speaks, but compared to some other things we're trying to do, this is relatively easy. They are also relatively easy to operate. You do single qubit gates here by just doing a microwave pulse. We are blessed with microwave engineering done for, let's say, Wi-Fi and 5G technologies for the last, I don't know, 40 years. So we can buy very good microwave generators, and those have phase stabilities that are good enough such that we can just do gates on these. And they're relatively easy to scale in the sense we can just make many of these next to each other. And this is sort of what people have done all around the world. So here's a few examples of how superconducting qubits look when you look around the world from some of the big players in the field. So here's an IBM quantum computer with, if you squint, you can see that it says 133 qubits on the chip. You also have Google's Willow, which I think is 101 qubits. And at University of Science and Technology in China, they have also 100-ish qubits on their qubits. I will not try to pronounce what it says here, but for those of you who does speak Chinese, you can probably find the name of the chip there. One thing you notice about these common pictures from some of the big players is when you look at it, they actually look a little bit blurry, which is on purpose, because usually these companies don't want to tell you what they make. So that's why we make our own devices. And when we make our own devices, so for example, one that we made at ETH in Zurich with 17 qubits, or some of the newer stuff we are making in Delft, so we can zoom in to the level that we want. We can take SEM images, we can take very high resolution optical images, and we can really explain everything we do. So that's what I will try to do today, and highlight some of the features that you need on your superconducting qubit chip. Just flashing this, just put a few numbers off. So if you're not so familiar with superconducting qubits, you may wonder where is the field sort of currently at. And these are sort of good numbers to keep in mind. So the first thing to always think about is coherence times. And for superconducting qubits, state of the art is around 1 millisecond. And there's a few different groups that have achieved this, both with traditional transmon qubits, but also with something called a fluxonium qubit. I will talk about that a little bit in a bit. Single qubit gates, I think most people can manage to get 99.9 these days, and some groups have pushed this very close to 99.9 and slightly beyond. So this is where you can do the best at single qubit gates. And very recently, 2 qubit gates have also reached the 99.9 regime in sort of 3 different groups. Here showing the plot from IQM's paper. Where they measured also, they just measured the fidelity of their CZ gate over 40 hours, just to show that this is not just a random number, this is a systematic number that they just have. So they get this 99.94% fidelity for their 2 qubit gate over 40 hours. So this is, I would say, currently the best data on 2 qubit gates in the field. Okay, these are just numbers, but what actually matters is how do you put all of this together. And if you look at state of the art for superconducting qubits, there's sort of 2 things we can think about. There's the what do we actually do with them, and then there's the actual goal that we want, which is quantum error correction. I picked just a random paper that I liked from a few months ago, done on IBM hardware by some researchers from Spain, where they did a high energy physics simulation on this 144 qubit processor. I'm not going to pretend that I understand high energy physics, but I think it's still very impressive that they can do these type of what looks like very, very complicated physics calculations on hardware done with a quantum computer. And I would say that this is now at the level where I think we all need to start asking ourselves, at least if you are doing a, let's say, PhD in theoretical condensed matter physics or high energy physics, in a few years from now, I think you should ask yourself the question, is it easier for me to learn how to do complicated tensor network calculations, or is it easier for me to just run it on IBM's hardware? And I don't think the answer 2 years from now is going to be obvious. And I think that's pretty cool. It's still pretty far from sort of economic impact, but as a physicist, I do think it's very cool. The second application that I think we should think about is quantum error correction, because as I said, the only way we actually get to where we want at the end is quantum error correction. And this is sort of state of the art for quantum error correction. From Google, they used 101 qubits to do a surface code quantum error correction scheme. And they showed that when they make the surface code bigger and bigger, the errors go down. And that's what you want to do, because lower errors is where you want to go. And if you can do it by just adding more qubits, then eventually you will win. So that's what they showed, and it looks very, very impressive. And I want to focus a little bit more on quantum error correction, because as I said, we need it at the end. So if we are building new hardware, and that's what we are doing in my lab, and also in many of the talks in this conference is focused on building new types of qubits. If it's not going to work to do quantum error correction, you should not pursue that platform. That's maybe a message I also want to say. If you want to build new qubits or new hardware platforms, it needs to be able to do quantum error correction. If it can't, for some reason, maybe you cannot do mid-circuit measurements in the platform you're thinking, then it's no good. Do another platform. I think most people here appreciate that fact, but I still think it's important to mention. So let me do a slight detour in thinking about when I say it needs to do quantum error correction, what do I actually mean? I mean we need to be able to do parity measurements, meaning if you think about a very, very simple error correction code, the bit flip code where we have a logical 0 in the 0, 0, 0 state, a logical 1 in the 1, 1, 1 state. We need to be able to detect if there's errors in this logical subspace, and we do that with the circuit that is shown here. So we do a couple of 2-qubit gates, and then we measure these extra auxiliary qubits here in the middle. And then we need to repeat this again and again to see if we get errors. And then this auxiliary qubit always need to be reset to the 0 state, and the result is essentially the outcome of measuring these so-called stabilizers here, which are the stabilizers for this bit flip code. So the Z, or the Z1, Z2, or the Z2, Z3. So this is the basic building block of any error correction code, which means that if you go to the surface code, it's the same thing, but slightly more complicated. So in surface code, your qubit is on a surface, on a 2D grid, which is of dimensions d times d. And the stabilizers are these now what we call weight 4 stabilizers, which means you have 4 qubits in each stabilizers, and either you measure Z, 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 or you measure X, 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 which you can do by doing these circuits here. So the blue qubit here, or the green qubit here, are our auxiliary qubits, and we have the yellow qubits here as the data qubits that sit on this 2D grid. And if we lay that out, for example, as a so-called distance 5 code, it will look like this. And if you're very quick at counting, you will count that here we have 49 qubits, which is the number of qubits to do this type of codes. And then what you do is you do these 4 circuits for all the, I keep doing this, I should do this, for all these squares, blue squares and the green squares, you need to do these type of circuits again and again and again when you do error correction. So this is the type of thing we need to do. So if you want to build hardware that can do this, I want to highlight this work we did at ETH, which was the first device that did repeated error correction with the surface code. And there we built, there was distance 3 code, so that's 17 qubits. And the chip for that looks like this. And we can zoom in, and if we zoom in, it looks like this. And actually here we have all the basic building blocks that you need basically for a superconducting qubit processor. So what you see in these yellow star-shaped figures here, those are actually our qubits. So the yellow part is a very big capacitor plate that has a big capacitance to ground. You notice the shape is a little bit funny, it's like star-shaped, and that's because we have these requirements from the error correction code on how we connect, right? So we need, each qubit needs to have at least 4 neighbors, right? Because we need it on a 2D grid. We also need to do readout of these qubits, right? Because we need to do the mid-circuit measurements, and also at the very end, we need to read out the qubits. And then we also need to be able to tune the qubits with the flux. So as I mentioned before, we often do this squid loop, and then we spread a flux through this loop, and we need also to do that. So there also needs to be space for that. And then finally, we need to have space for also driving the single qubit gate, which is you send in a microwave pulse. And all these elements are here. So the yellow part, as I said, is the qubits. The sort of turquoise bluish connection here are the couplers that connects the qubits. The red part is a resonator, so think of it just as an LC circuit, but stretched out as a coplanar waveguide resonator, which is what we use for readout. Fun fact is you notice that there's also a blue resonator here sitting next to it. That's something that we call a Purcell filter that makes readout fast without introducing extra errors. And that's something that also, for example, IBM and Google use on their chips. There are sort of 2 ways you can do it. You can do it as we developed at ETH, where you have 1 Purcell filter per qubit, or you can multiplex it, which is kind of what Google is doing, and have multiple measurements per Purcell filter. When you do that, the second thing that Google does, actually it becomes a little bit tricky because then you have more crosstalk. And Google recently did, not their surface code experiment, but they also did a color code experiment. Because they designed the chip for the surface code, they had laid out all their readout resonators such that you can do the surface code. But because they chose their readout in a way that they didn't optimize sort of more abstractly, they actually had a lot of readout crosstalk for their color code because now they needed to use things differently. So that was a challenge. So that's just to say that the choices you make when you build your chip will come and catch up to you if you try to do shortcuts. Then finally, I want to mention the control lines. So we have the green lines and the pink lines. The green lines are the flux lines to tune the qubits, and we also use it for 2-qubit gates, because the way we do 2-qubit gates in this experiment was we tuned the frequency on 1 qubit to get it into resonance with another and tune back again. And the pink line is the single qubit drive lines. And so we can build this, and in principle, we could just make it bigger, right, and go up to 1 million qubits like this. But I would say that this is maybe not obvious if we can just do that. So we would like to do something else. And before really getting into how to build different hardware, let me briefly mention that actually you could also do something smarter on the error correction side. So instead of doing the surface code, something that's very popular currently, and I think we're going to see a lot of nice results on that in the coming years, is to design what is called quantum LDPC codes, which stands for low density parity check codes. In fact, I think you're all using low density parity check codes daily because this is the type of code that Bluetooth is using. So if you're using Bluetooth, you are probably using LDPC codes. The quantum version of it are predicted to be much better than the surface code in that it requires maybe a roughly factor of 10 less qubits. And a very concrete proposal is this device here, or proposal from IBM, which requires 144 physical qubits to encode 12 logical qubits, which is pretty good. As you see, all the qubits are on this 2D grid, similar to a surface code. But the key thing that makes this slightly more complicated is that you have these lines here. And in fact, it's a little bit misleading here, because what you should actually think of is that this square here that connects also like the qubits like this should be superimposed on every single qubit. So if I pick any other qubit here, you should also think of it as having a connection to this, which has a connection to this, which has a connection to this, which has a connection back to where I started. So this is sort of misleading. So this means that actually you have a lot of connections here. And if you want to lay that out on a chip, this is a picture from IBM of their CAD layout for their chip that implements this. It looks a little bit complicated. So the blue parts are the pockets for the qubits, and then you see all these red lines, which are all the connections to do these, all connections both to nearest neighbor and also to these what we call long distance couplers. And you notice that maybe it's a little bit hard on this screen, but you notice that maybe there's like 4 different shades of red. That's because each shade of red is actually on a different physical layer. And then you have a qubit layer and you have a readout layer. So actually, you need 6 layers of wiring, which means a flip chip on top of a chip flip on top of a flip chip to implement this. And also, you need to now make your transmon even more complicated, because now each transmon needs to connect to 6 neighbors, not just 4. So already, when I showed our device, we connected to 4 neighbors, looked a little bit complicated. Now you need to do it to 6 neighbors. So this, I think, looks a little bit complicated, but I'm really happy that IBM is pursuing this on a serious level. If you want to do something simpler that you can maybe do in your lab in the next few years, we made a preprint earlier this year where we designed quantum LDPC codes that we think are easier to implement on near-term hardware. Here's an example of how you would lay it out on a superconducting qubit chip. And since there's a lot of spin qubit people in the room also, if you go and check the preprint, we also have a very concrete proposal on how you can do it for spin qubits using the modern shuttling techniques that people have looked at. Coming back to the qubits themselves, how can we improve the qubits? And there's sort of a different range of things you can do. You can maybe try to sort of incrementally improve the qubits, or you can sort of throw a curveball and hope that it gets much better. And in our lab, we sort of pursue sort of this spectrum of things. Of the things that are maybe just a slight modification of the transmon is this fluxonium qubits that I mentioned before. So in a transmon, you have a capacitor, you have a Josephson junction, and what you add in the fluxonium is another inductor. So you have 3 elements. Which actually adds a surprising amount of flexibility in designing the qubits. And recently we showed that we can also do very fast, high-fidelity 2-qubit gates with this fluxonium architecture, which for a long time was an open question. And yes, the other thing, which is maybe on the other side of the spectrum here, is the so-called Kitaev transmon. Here we don't have any experimental results yet, so I'm just putting the theory paper from the group of Ramon Aguado, who also gave a nice presentation about that yesterday in the hybrid session. So here the idea is to take some of the ideas that Leo presented yesterday on how to build Kitaev chains, and we can embed that into a transmon, and at least on paper, this should give us pretty good qubits. I will come back to a little bit more at the very end. The final thing that I want to mention is sort of in the middle, which is what I will talk about for the rest of this talk, is what we call Andreev spin qubits, which tries to take some of the things we like about superconducting qubits and combine it with some of the things we like about spin qubits. So how does that work? So to take a step back, let's go back to our Josephson junction. So we had a superconductor, an insulator in the middle, and then a superconductor. Now what we can do is we can exchange this insulator with a semiconductor. And then when you have a semiconductor in proximity with a superconductor, you get a lot of very nice physics. The sort of basic thing you should think of is something called the Andreev reflection. So if you have a metal, and for our intents and purposes, I know semiconductor physics is more complicated, but for our intents and purposes, a semiconductor here is really just a gate-tunable piece of metal, normal metal. So in metals, you have electron traveling, right? That's how you carry current. And then if you then have an electron and it travels and hits a superconductor, then if you go into a superconductor, it would need to be transformed into a Cooper pair, right? And if you have one electron going into one Cooper pair, you need a reflection of a hole to have things preserved, right? And then if you can do the same on the other side, then you get sort of a electron-hole pair that sort of gets trapped in here. We call that an Andreev bound state. And this is the type of physics that we like to think about here. And that's also why we call this Andreev spin qubits by inheriting that name. The thing you can also do just to make it slightly more easy to work with is you can confine this Andreev bound state a little bit more such that it effectively works as a quantum dot. So we have a superconducting quantum dot superconducting junction. Such that we can really trap a single excitation in this Andreev bound state. And if we do that, we can actually address the spin of this fermionic degree of freedom. And that's what we will use as an Andreev spin qubits. If we just look at this superconducting quantum dots superconducting junction, there's a lot of nice physics you can do. So if we want to implement that in an experiment, the way we do it is we take these indium arsenide nanowires. When we get them from our collaborators in Copenhagen, they're covered with aluminum on the shell. So when we put them on our circuits, what we do is we etch away a little bit of this aluminum, and then you have sort of exposed indium arsenide here in the middle, which is our semiconductor, and then we have aluminum out here. We have put this on top. We have put this on top of these gates that sit below, and we can use now these gates to define the quantum dots. And then we put this into a transmon qubit. So here we have a capacitor, a standard Josephson junction, and then we have this quantum dot. And what we can do is we can then do spectroscopy of this system. Standard ways you would do it for a transmon. If you look on the top, this looks like a normal asymmetric transmon. This is the case where the Andreev bound state is empty. Then we can tune the thing to fill up a single excitation inside of this quantum dot. One thing you first notice is that that's actually pretty nice, is that up here we have maximum going to minimum. Here we have minimum going to maximum. So actually we have this pi shifts because the junction of the quantum dot, when you have a doublet excitation in it, it's actually a pi junction. So that's some nice physics there. But what you see also in spectroscopy is that we actually can address the spins of these systems. So if we do that, we can also drive Rabi oscillations, for example, on this spin qubit. And if we measure coherence times, we get sort of what I would say a pretty good lifetime. But the coherence time is maybe not very good. So we have 11 nanoseconds, which is not great. But we also understand why, and that's because this material, indium arsenide, couples very strongly, or the spin of this couples very strongly to the nuclear bath of indium and arsenide. But regardless, we can still scale this up. So if we put two of these in two different loops, which looks like this, so you have a loop here, and you have another loop here, then you can connect two Andreev spin qubits together with one junction, and then you can use that to have strong coupling between the two Andreev spin qubits. So here we get spin-spin coupling on the order of 100 megahertz, give or take, and we can tune it to 0, so we really have a tunable coupling, which is a strong coupling between spin qubits in this system. And we also think we can scale this, so if we just keep making more and more loops, we actually get all of these spin qubits can talk to each other. So we have this platform where we can do all-to-all connectivity, and we can tune all of the different couplings. In this paper here, we really go through all the details on how you would engineer this. But the key thing really just keep adding loops of loops. And in each loop, you have one Andreev spin qubits. You have the flux here that can control the couplings and so on. And you can calculate that you get very sizable couplings. You get very strong, good on-off ratio. And then you can build these like big spin networks of this if you sort of turn all the couplings on or selectively on and off, depending on what you want. And we think this could be a nice platform to explore sort of spin model simulators. And because you have this high connectivity by default, maybe it's also interesting to explore some of these quantum LDPC codes. Some of the technical challenges here, of course, I mentioned we have not great coherence, and one of the things we want to do in the future is to change from indium arsenide to germanium. And Menno Feldhorst yesterday gave a nice presentation on germanium spin qubits. They have pretty good coherence times, so we should ideally be able to replicate that. Adding all of these loops also adds a little bit of complication. To make device design easier, we also want to move to a flip chip architecture. We are developing that for this hybrid system together with the group of Sridhar Goswami. So here's an example of how that looks. And then we can also go a little bit more crazy. And I want to go back because now I said, okay, superconducting qubits, they are limited mostly actually by dielectric loss, meaning you're coupling to charge operator. These Andreas spin qubits are limited by their spin degree of freedom coupling to things. So if you want things that are as good as possible, ideally you would want a qubit degree of freedom which is chargeless and spinless, right? And one idea for that is to have these Majorana modes in Kitaev chains. So that's sort of the motivation of adding more of these quantum dots into the transmon in a way that we can engineer Kitaev chain. Then at least we should not be limited by charge noise and flux noise, spin noise. And at least on paper, we should then just be limited by quasi-particle poisoning, which for very well-engineered systems have been shown to be up to seconds in superconducting qubits. So with that, I want to thank all the nice students in my team. On this conference, you will find Jinlun, Natasha, and Yenan. Yenan will be happy to talk about our work on this flip chip integration, Natasha on the Andreas spin qubits, and if you want to hear about the fluxoniums, talk to Jinlun. Thank you for your attention.
Thank you, Christian, for a nice talk. Talk is open for discussion. Any questions? I'm happy to start. So about the QLDPC codes. So my understanding, as you explained, is that you need more connections. Is that opening up like extra error channels, maybe even chance for correlated errors? Is it something you have to worry about when you move to QLDPC codes?
Yes, that is something you should worry about. But it's at least sort of on a very high level. It should always be better because you have some of the same let's say, guarantees as for service code, that as long as the correlated errors is not bad enough or not too bad, you can deal with it by maybe extra rounds of error correction. But it's something you should worry about. And I think this is also one of the motivations that we had really for proposing to do some of these small LDPC codes. Because you need to, in a specific architecture, if you're building it, you need to see how does the errors actually or what errors actually arise, and how do we deal with them in a practice. And I think building a chip with 144 qubits is very ambitious if you want to see the errors sort of nicely behaved. So by building some of these small quantum LDPC codes, I do think that we can try to test some of these things. Is the errors nice enough, so to say?
Thanks.
Okay, thanks. So my question would be that, okay, if you manage to make, let's say, your 10,000 qubits, or someone would manage, what's your take on the scalability of all the, instrumentation or things like this around? Not just cabling, but just in short. Yeah.
Yes, good question. I think you need to think very hard about it. I do think that some companies have sort of as a proof of principle built electronic racks that can do 1,000 qubits. I don't think it's unfeasible that they can do 10,000 qubits. It's going to take a lot of electrical power, but I do think you can brute force the current electronics to 10,000. To 100,000, I'm less sure. And to 1 million, I do think you need to really rethink how you're doing your control.
Thanks. Further questions?
Yeah, thanks for the nice talk. So you mentioned that IBM and also you use flip chip techniques, and you know, what are the limitations and challenges if you want to have that?
On the flip chip?
Yeah.
Yes, yes. So you need. So the way you typically do flip chip is that you need to put indium on your chip, and then you bond by pressing this. It's actually a technique that is very well known from the classical electronics industry. If you take your phone, all of you actually have flip chip technology in your phone. Your camera chip is flip chipped to the motherboard of your computer. So the techniques on how to do good flip chips is well established. The challenge for superconducting qubits is you need to make sure that it's a good superconductor. So it needs to make sure that the indium bombs that you make are pristine enough such that they are still superconductors and they don't add any dielectric loss. So you cannot have resist stuck to it and things like this. And some of the cleaning methods and process methods that you use in traditional industry are not compatible with the standard superconducting qubit fab. So you really need to think about how do you make this indium bond in a way that you just have the indium and not any of these other residues that you would typically have in a sort of conventional flip chip process. But once you figure that out, I think it's not that difficult. I think at least that's what the results from IBM shows. They just do it now, and their qubits have a few hundred microseconds T1s, so it seems to work pretty well for them.
Thanks. We do have time for one more question. You can see Janos back.
So what would it take for fluxonium to be more popular than transmon?
I think in terms of performance, I think there's many good reasons for doing fluxoniums, but it still needs to show that it's credibly to scale it. And what I mean by that is things like, okay, if you have 2 fluxoniums, you can do a good qubit, right? But then you need a third fluxonium. And you need to make sure that this third fluxonium, if it's sort of a spectator to what happens here, does not introduce what we call spectator errors. And that's sort of an open question. And for example, if you take the strategy that at MIT, they developed a very, very beautiful 2-qubit gate for fluxoniums. But if you try to replicate that to 3, that doesn't work because that will introduce too many spectator errors. So you need to a little bit think about, okay, what are the coupling regimes you want to be in such that you can really controllably scale it in a way that each qubit is quote unquote localized and not sensitive to things that happen on the other side of the chip.
Thanks. Maybe a final question, we still have time. I can ask one a clarification question about the one-dimensional like scaling up architecture of the Andreev qubits.
Yes.
So is this, maybe you said this, but is this an all-to-all connectivity architecture?
Yes, it's an all-to-all connectivity architecture.
Okay, and how does it work? So what are the tuning knobs you have to play with to make a 2-qubit gate between distant patches? Or
yes, so maybe I can show this. So essentially, I skipped over that a little bit quickly, but essentially, in each loop, if the accumulated flux in each loop is a multiple of pi half, then the spin qubit doesn't couple to the supercurrent across it. While if it's pi or 0, the supercurrent couples to it. And then if you go in between, you can essentially tune from anywhere from 0 to your maximum coupling.
And you can activate pair interactions?
Yeah, so then
one by one.
Exactly. So all of them couple pairwise to each other, essentially. So you can either turn on all of them, and then you essentially have, let's say, an Ising model where everything talks to everything, or you can pairwise turn them on and off, and you can then do 2-qubit gates. That depends a little bit on what type of interactions you want to implement, but it is always pairwise.
Thanks a lot. Let's thank Christian again. And we move on to the second plenary talk of the session. This is going to be given by Michael Kastoryano, who is an associate professor of quantum computing at the University of Copenhagen and an Amazon visiting academic at the Amazon Web Services Center for Quantum Computing. Michael obtained his PhD in quantum information theory from the Niels Bohr Institute in Copenhagen in 2012, and then he was a junior research professor at the University of Cologne for a few years before moving back to Copenhagen. His primary research interests are in quantum algorithms and the tensor networks with applications in physics, machine learning, finance, and engineering. And today, Michael will tell us about quantum Gibbs sampling algorithms. Michael, thanks for coming and looking forward to the talk.
Thank you. Thanks for the invitation. This is quite a nice room. So what I want to talk about today is sort of the culmination of a longer research process that started almost 12 or 13 years ago. So it's quite exciting. Originally, it started, well, with a number of people, but the main actors have been Fernando Brandão back then, and then Anthony Chen and Andres Gillian, who should be in the audience, who've really been pushing it. So to start with, I want to talk a little bit about the classical theory. And the setting we want to consider is standard statistical mechanics, which means you have a probability distribution, pi, on a discrete space, in this case just binary space. And it's going to live typically on a lattice, although it doesn't have to. And the thing is that you have some prescription for this probability distribution because it's living on an exponentially large space. Then even sampling from this distribution or inferring any properties of this distribution can be a very challenging task. And the idea of Monte Carlo is, instead of trying to build the distribution directly, which would be very difficult since it's an exponentially large vector, you build a probability transition matrix such that as you iterate this probability transition matrix, you converge to the state pi that you desire, right? And this should be true for any configuration that you start in. Now, this sounds a bit crazy because the matrix that you're iterating is squared larger than the vector that you're interested in. But it turns out that if you have sufficient amount of structure in your problem, then this matrix can be constructed implicitly in such a way that you can, again, implicitly have access to samples from the distribution, right? And this is the basic idea behind Markov chain Monte Carlo. And the key mathematical properties associated with this process are: A, your process has to be ergodic, meaning it has to visit, at least in principle, every single point in your phase space. And the second property is that it has to satisfy detailed balance. And the detailed balance condition is a mathematical condition which basically says intuitively that processes that go forward in time are identical to the similar processes going backwards in time. If you are able to produce this type of an algorithm, the key questions are, on the one hand, can you prepare Q efficiently, right? Can this implicit process be efficient for each step? And then the second question is, how many steps do you actually have to perform before you converge to the desired state, or at least until you get very close to the desired state? And Markov chain Monte Carlo has many, many famous applications. It has its roots in statistical mechanics, in fact, in the Manhattan Project. But later, it had plenty of applications in theoretical computer science and many, many in industry. So oftentimes, when you're performing some type of simulation, you're going to invoke the Monte Carlo procedure in some way or another. So in particular, in the case of statistical mechanics, there's a go-to algorithm called the Metropolis-Hastings algorithm. And it's for problems which have this additional structure, which is that the state you're looking for is a Gibbs state of a Hamiltonian, and your Hamiltonian lives on a graph that's not too connected. And if you have this type of structure in your problem, then the Metropolis-Hastings algorithm has the following prescription. So first, you perform an exploratory update. And this exploratory update, in case of spins on a lattice is you pick a spin, you flip it. Then you pick another spin and you flip that. Then you pick another spin and you flip that. And it's not difficult to imagine that by performing this operation, in principle, you explore all of phase space. So it's ergodic. The second rule is that for each, so you have a configuration, you evaluate its energy, and that's an efficient procedure because you have the prescription of a local Hamiltonian. You flip one spin, and then you evaluate the energy again. And then you calculate the energy difference. And if the energy has gone down, you accept the update. If the energy has gone up, you accept it, but only with a probability which is proportional to the ratio of, well, this is proportional to the exponential of the energy difference. Right? On top of that, if you're dealing with a local Hamiltonian, then this energy difference is a local quantity which can be computed very efficiently. It turns out that this procedure satisfies this detailed balance condition, and this detailed balance condition guarantees that your unique stationary state is the thermal or Gibbs state of the Hamiltonian, right? So the first step guarantees ergodicity, and the second step guarantees that your unique stationary state is the desired state, right? So the remaining question is typically, can you evaluate the ratio efficiently? And this you can do as long as the Hamiltonian is sufficiently local. And then the much harder question is, does this map converge rapidly? How many iterations do you need to perform before you eventually get very close to the stationary state? That's the so-called mixing time. I'll need this later, so you don't have to, I don't want to go into too much details of this, but the Metropolis algorithm is typically described in a discrete manner. You update the state space one by one. It's sometimes more convenient mathematically to talk about the continuous version, right, where you have a continuous update, so an update according to a continuous parameter, which is time, of a semigroup. And this is relevant because there's a very close connection between the mathematical structure of the probability transition matrix of Markov chain, which is that the columns have to sum to 1, and the generator, this L matrix of a semigroup, right? So what the structure of L has to guarantee is that for any choice of T, P of T is a probability transition matrix, meaning that its columns have to sum to 1. And the specific structure of L is that all of its non-diagonal entries on the column have to be positive, and then the diagonal has to be negative, and the sum has to go to 0. Okay. It turns out that in the quantum setting, it's much easier to translate the continuous formulation than the discrete formulation. For those of you who know stochastic differential equations, the way to think about this is that the continuous formulation is a bit like a Fokker-Planck equation, whereas the discrete formulation is a discretization of the stochastic differential equation. So to be a bit more practical, and something you've probably seen in some statistical mechanics lecture at some point, you consider an Ising model, so it's Hamiltonian on a lattice where nearest neighbors interact with a negative interaction, so that the lowest energy states are the ones where all spins are aligned. And you put the system on a two-dimensional lattice, for instance, and what's very well known is that if you're at high enough temperatures, so if the coefficient of the Gibbs state beta is small enough, then you're going to have a disordered distribution. And as you lower and lower and lower the temperature, at some point, you get to an ordered distribution, and if you're at sufficiently low energy, then the system wants to be either in the all-up state or in the all-down state. Okay? So there's a phase transition that you cross at a certain temperature, and this temperature is known. And one of the features that you can measure of your system as you cross the phase transition are two-point correlation functions. So if you're at high enough temperature and you measure this spin, and you find that in the upstate, there's no reason to expect that this spin that's far away is going to be in the upstate. On the other hand, if you're at very, very low temperatures, because you want to be either in the all-up state or in the all-down state, if you measure this spin on one side of the lattice in the upstate, you expect a spin arbitrarily far away to also be in the upstate, and similar down. This is interesting because the Metropolis Monte Carlo algorithm is a dynamic procedure, right? So you talk about dynamics in time, whereas analysis of statistical mechanics models typically is a static procedure. You're talking about what are the correlations in your system. So it was realized over 30 years ago, so what was realized is that there's a one-to-one connection between the continuous Metropolis algorithm, so the dynamics in time, and the correlations in space. And the way this one-to-one correspondence goes is that if you have a statistical mechanics system, right, which what I mean by that is just a Gibbs state, and you know that it has exponentially decaying correlations in space, then you're guaranteed that its natural continuous Metropolis algorithm is going to be rapidly mixing in time. Conversely, if the Metropolis algorithm is rapidly mixing in time, then you're guaranteed that its static property, so its Gibbs state, has exponentially decaying correlation. So it's a one-to-one correspondence, and it's a very rich mathematical theory, which has been subsequently been developed further in all sorts of directions. In particular, there's a very rich network of equivalences. I guess I don't want to go too much into this detail, into the details of this, but it'll be useful to talk about the extensions to the quantum case. Good. Applications of Monte Carlo are extremely widespread, right? So in classical physics and chemistry, we use them all over the place. In optimization problems, we often use them in combination, typically with some type of annealing schedule. They're used in data science and variational inference, graphical models, and typically in computer science. If you then grow the umbrella to involve stochastic differential equations, which are really the diffusion cousins of Monte Carlo, then it expands to computational finance, machine learning. So it's a very large umbrella of algorithms. And why is it desirable to have a quantum Metropolis algorithm? Almost seems obvious in this setting, right? Some of the two major classes of problems where we expect a substantial quantum speedup, being problems related to cryptography and problems related to simulation, it seems quite obvious that we'd like to have a quantum analog of the classical Metropolis algorithm, which is the dominant algorithm for simulations for classical problems, right? So how does the quantum theory work? There's a dictionary to go from classical statistical mechanics problems to quantum statistical mechanics problems. And the dictionary goes as follows. So a classical probability vector gets mapped to a density matrix, so a positive semi-definite matrix with trace 1. An energy functional gets mapped naturally to a quantum Hamiltonian. A Markov chain gets mapped to a CPTP map. And what you should retain from that is that this special condition of stochastic matrices where the columns have to sum to 1 gets mapped to the fact that a CPTP map has to have the structure where it's a sum of Krauss operators that act as K and K dagger on each side of rho. And then in the continuous setting, this condition of the columns having to sum to 0 get mapped to what's called a Lindblad-Master equation. And the Lindblad-Master equation is an operator acting on rho, which has this very specific form. So it has a Hermitian element H, and then jump operators, like a CPTP map, and then this extra term. What has to be retained is that if you, for any choices of a Hermitian H, and arbitrary, not necessarily Hermitian L's, if you plug them in this particular form, then you obtain the generator of a completely positive semigroup. So e to the IL is going to be a CPTP map. Okay, so it's an if and only if. And then finally, this detailed balance condition can also be mapped to a type of quantum detailed balance condition, which is a bit more involved in its structure. Good, so let's try to rethink what metropolis algorithm should look like in the quantum setting. Right, so now we consider a quantum Hamiltonian, and just for convenience, I'm writing down a transverse field Ising model. Where now intentionally there have to be Z Pauli operators interacting between points in the graph, and then an X operator on the single sites, just to make the Hamiltonian not completely classical. And then what we're interested in is in the Gibbs state of this particular model, right? But now there's one core crucial difference, or at least one core crucial difference, which is that eigenstates of the classical model are basis states of your state space. But eigenstates of the quantum model can be highly entangled across all the states. But the Gibbs state is going to be a Gibbs distribution over eigenstates, right? And that's where all the difference really comes in. But anyway, we'll try to replicate the procedure, the prescription for the classical metropolis algorithm, and that has to do with starting with an exploratory channel, and that typically would be you pick a spin or a qubit now, and you perform one Pauli flip. It's not enough just to flip the spin, but you need to choose either an X flip or a Z flip. That's simple enough. It's going to be ergodic. And then the next step should be, well, you calculate the energy of the configuration before you perform the flip. You calculate the energy of the configuration after you perform the flip. This is still a well-defined quantity. If the energy goes down, you accept the flip. If the energy goes up, you only accept it with a probability which is going to be proportional to this Gibbs factor. Okay? You can consider this as a weighted walk on Hilbert space. And in particular, you can show that it satisfies this condition of detailed balance, right? So you think, okay, that's great. That was pretty easy. But there are at least two substantial challenges here. And the first, I wrote them in different order. The first is that the no cloning theorem doesn't allow you to compute the energy and then accept or reject it, right? So somehow you would need to hold a copy of the state, but you're not allowed to hold a copy of the state because of the no cloning principle. And the second, which turns out to be the much more substantial challenge, is that because eigenstates of a classical Hamiltonian are basis states, then differences in eigenenergies have to be discrete, right? On the other hand, in the quantum setting, energies, especially if you have a non-commuting Hamiltonian, can be very dense, right? So the spectral range of a Hamiltonian is a polynomial in the number of qubits, but the number of states is exponential, right? So at some point you should expect, unless you have a lot of structure, like a commuting Hamiltonian, you should expect places where you have a very, very, very dense spectrum. Okay? And on top of that, meaning exponentially close, and on top of that you have absolutely no promise that eigenstates that are very close in energy are close in entanglement structure. So you can have eigenstates which are very close in energy but have completely different entanglement structure. So jumping from one to the other, which should be a very easy process classically, can be a very, very difficult process quantumly. There was a proposal in 2010, a very popular proposal by Teme and collaborators, which proposed to use the Marriott-Watches trick to solve the accept-reject step. And then they proposed something, this is a technical element, something called the shift invariant boosted phase estimation for the precise energy estimation part. Okay? Clearly, you won't be able to estimate to exponential precision the energy difference between states, right? But there might be workarounds. And this was in 2010, and I think, and for a long time, this was very much accepted as the quantum algorithm for Gibbs sampling, or the quantum metropolis algorithm. Although it wasn't really used very much in practice because it was a very cumbersome algorithm and was a very difficult algorithm to analyze. It turns out that in 2023 we found a fundamental flaw in this step. Okay, but it took until 2023 where it was basically accepted, and we considered this theory roughly finished, at least from a practical perspective. And most of the focus in the field turned not so much to the practical algorithmic aspects of quantum metropolis sampling, but more to the mathematical aspects. And then there was a great deal of flurry of activity in the mathematical aspects. And in particular, so what I was involved in very much also with Christian Temme is first developing this theory of mixing times for quantum Markov processes. In particular, understanding this connection between temporal and spatial mixing. And later, there was a theory called Log-Sobolev, which really sharpens ideas of mixing. Other communities worked more on transport problems. There turned out to be a very intimate connection between entropic quantities like conditional mutual information, recovery maps, and Gibbs sampling problems. That was also a very active field, still is an active field. But somehow all of the rigorous results of actual problems involving Gibbs states only seem to hold for commuting models, right? In particular, somehow we were the only existing practical model for Gibbs sampling. So this L operator we only knew the construction for commuting Hamiltonians. So most of the work on Log-Sobolev inequalities and mixing times only really worked for commuting models. So somehow there was a disconnect between what was supposed to be a completely general metropolis algorithm and all of the mathematical results. And you know, in retrospect, now we understand this by the fact that this original quantum metropolis algorithm really wasn't the right one. Okay. And so the end result of what I'm going to talk about is how we finally landed on the right theory of a quantum metropolis algorithm. But to do that, what I want to do is I want to take a step back and think about physics for a second. Because up to now, what we were discussing are algorithmic constructions, which are in principle synthetic. They don't necessarily have to have anything to do with physics. But they somehow do, at least in words, claim to pertain to thermal systems. Okay, so let's think of how systems actually thermalize in nature. And this is a vast question. There's a lot of research working on it. But one of the standard models that's used is this weak system bath coupling. So you consider a finite system described by Hamiltonian H that's coupled to a large thermal bath described by Hamiltonian B. And the system and bath are coupled by some operators. And these operators are not so important, but they have to span the operator subspace of the system. The bath is assumed to be in a thermal distribution, and it's assumed to couple very weakly to the system, right? And somehow this weak system-bath interaction should make the system relax to a Gibbs state. And we have a standard approach for this, which is saying that if the bath is completely forgetful, right, so no information that seeps out of the system into the bath ever comes back into the system, or if the bath refreshes sufficiently fast, and this is the key caveat, if this coupling term is smaller than any energy gap in the system, right? So here's again this thing of the system can't have too small energy gaps in its spectrum. Then you can show that the open system dynamics on the system, when you trace out the bath, is given by this Lindbladi, okay, so the specific structure. And in particular, this structure is called a Davies master equation, so we know the details of the operators involved. And in particular, the operator, the jump operators here, but one can ignore the Hamiltonian terms. The jump operators, I don't know if I can get this out here, involve a type of operator Fourier transform on the bare local couplings, right? So the bare local couplings A sub A are going to be the Pauli flips, and then you dress the Pauli flips by some operator Fourier transform with a particular frequency omega, and this frequency omega is going to be all of the energy differences in your spectrum, right? So you have to sum over all the energy differences, and then you have to build all of these jump operators, okay? Of course, nature does this naturally. And then what you can show is as long as this quantity gamma, which is related to the Bath correlation functions in the original system Bath description, satisfies this mathematical property, then it guarantees that your semigroup satisfies detailed balance. And if your semigroup satisfies detailed balance, you're guaranteed that the stationary state is the Gibbs state. Okay, so now we have a setup where we have explicit jump operators which guarantee that we can prepare a Gibbs state. Which philosophically is a bit interesting, right? Because Metropolis was introduced in a completely synthetic manner, and then when we adapt the Metropolis, and it's worth saying, if you're working with a purely classical system, then this Davies-Masters equation completely reduces to the continuous Metropolis algorithm. Which is interesting, right? Because Metropolis algorithm was introduced completely synthetically, and it's by a derivation through quantum physics, right, that somehow we were able to rigorously connect the Metropolis algorithm to a physical process. So I might, yeah. So I guess what I want to say here is that you might already see that there's a potential issue popping up, which is that if you take a local Pauli operator on your lattice and you conjugate it with the Hamiltonians on both sides, the Hamiltonian is a completely non-local operator, or at least the exponential of a Hamiltonian is a completely non-local operator. So that if your Hamiltonian is not commuting, then each jump operator is potentially going to be completely non-local. Right? So in the special case where your Hamiltonian is local on the lattice and has commuting terms, which means that the terms in the Hamiltonian itself commute with each other, then the terms of the Hamiltonian that don't interact with A will sort of cancel out. Right? And you're only left with a local jump operator. And indeed, for commuting Hamiltonians, this is coming back to what I was saying about there was a detailed description of this statics versus dynamics correspondence. We were able to use the Davies-Masters equations for commuting Hamiltonians to really reproduce all of the classical results, with some caveats, but they mostly hold. But as soon as you have non-commuting problems, everything breaks down. Yeah, it's worth saying that these played an important role and are still playing an important role for the analysis of self-correcting quantum memories. So that's maybe one of the most practical applications within the quantum physics community right now. So how can we salvage the problem in the quantum setting? Right? We have exponentially small gaps in the Hamiltonian, which means that somehow you can't truncate these jump operators effectively. But what you could do, and this was our first attempt, is you take the jump operators and you add a damping term, right? The naive damping term you might want to add is a Gaussian, right? So as soon as you so as t gets larger, the extremities of the Hamiltonian here start get exponentially damped, well, more than exponentially damped, right? Which means that you can truncate the Hamiltonian at a finite range, and the error is going to be exponentially suppressed because of this damping term. Right? And that's completely legitimate, it works. The problem is that as soon as you add the damping term, you lose this detailed balance condition. And if you lose the detailed balance condition, you lose the promise that your stationary state is a Gibbs state. So you might be performing an operation which leads you to a completely different state than the one you're actually interested in. It turns out you can show that in a very special case where you're guaranteed that this non-local dynamics converges very, very rapidly, so in a time which is logarithmic in the volume, then this is a sufficient trick. But in all other cases, and most other cases are the interesting cases, this doesn't work. Okay? But what we finally realized, and the solution is surprisingly simple, is that in fact this damping trick does work. But it does work with a bit of fine-tuning. Okay? So the idea is you add, and this is our final construction, or at least the basis of our final construction. So if you add a damping term, which guarantees that your jump operators are going to be local, or effectively local, and you add a function gamma, remember this was the function which sort of governed the detailed balance condition, that has this particular form. In the end, what gamma has to be is a sum, even an infinite sum of Gaussians. And the Gaussians in gamma have to be related to the Gaussian f in some very fine-tuned manner. Then it tells you that this transition part is detailed balance. But the decay part is not yet detailed balance. And the remarkable piece of insight was that the portion of the decay part which was not detailed balance is Hermitian, or anti-Hermitian, which means that you can add a coherent term B, which has this particular form, which cancels the non-detailed balance part of the decay. Okay? And when you take the two together, you get a detailed balance semigroup. And on top, and if you look at the structure of these operators, because you have the damping term, you're guaranteed that your jump operators are local. And in the same way, the Hamiltonian is guaranteed to be local. So this simple trick, or seemingly simple trick, completely recovers all of the key properties that we were looking for in our quantum generalization of the metropolis algorithm. Since then, there have been a number of extensions. There are various ways of taking the continuous description and turning it into a practical quantum algorithm. In the meantime, there have been many extensions to pure states and other scenarios. I'd say one of the most interesting recent results was showing that in that physical derivation of the master equation, actually what you can show is that in an epsilon, so in these physical derivations you do a second order perturbation theory, and you throw away all terms that are of order epsilon squared. And what's been realized recently is that within that ball of epsilon squared, there are a lot of different theories that we hadn't noticed. And one of the theories that we hadn't identified, and it was shown in this recent paper, is almost the same as our semigroup. So somehow the synthetic construction that we came to turns out to be a very, very natural construction, and probably very, very close to the way nature actually thermalizes. And this is exciting because now it gives us really what I consider a complete theory. So we have a physical description of thermalization, so a derivation from basic physical principles. We have efficient quantum algorithms, and then we have a tool for the mathematical analysis of thermalization and of self-correction. So I think this is where I'll leave it. So the way the field is going now is looking into really practical simulation of this algorithm. It might be an advantage, it might be a disadvantage, but it's very difficult to simulate this, which means that eventually we're really going to need quantum computers to actually perform these types of simulations. on interesting physical systems. And personally, I'm very interested in this connection to self-correcting quantum numbers. I want to advertise some open positions, both at Amazon and the University of Copenhagen, and thanks for your attention.
Thank you very much. Talk is open for discussion.
So you mentioned several times the minimum gap in energy within your eigenstates. What happens in case of a degeneracy because you have symmetry of the problem? What can you do?
So are you talking about the gap of the Hamiltonian or the
of the eigenvalues of the Hamiltonian?
So the gap of the so you mean the gap in the smallest eigenvalue of the Hamiltonian to the next
if you have degeneracy.
So that comes into play mostly when you talk about very, very low temperatures. Right? So the relevant gap when it comes to mixing times is not the gap of the Hamiltonian, it's the gap of this superoperator L. And the gap of the Hamiltonian really comes into play when you're talking about very, very low temperatures. Because when you get to very, very, very low temperatures, the only thing that matters are the very low-lying eigenstates. But this doesn't affect the ergodicity, basically, of your map in any way.
Hi, thank you for a very nice talk. And I want to ask, to what extent are these engineered Hamiltonian terms are related to the renormalized system and the bus couplings? Because you have the name shift from the interactions between the system and bus. Yeah. And you hope in the weak coupling limits, you can reproduce the keep sampling from the nature's constructions.
Yeah. So in this derivation, so you can think of it either just as a synthetic algorithm, in which case you ignore it, or if you can think of it as a system-bath coupling derivation. In the system-bath coupling derivation, what you can show is that the Lamb shift is of the same order of magnitude as the correction term, okay? And both are basically of second order in perturbation theory, so they contribute very little to the dynamics.
So to the second order, is it exactly the same? I mean,
it's a perturbative argument, so you throw away elements of higher order, right? Yeah. And basically, up to elements of higher order, the strength of the Lamb shift and the strength of our correction term are going to be the same.
Okay, thank you very much.
Thank you. Janos?
When you introduced the quantum version of the Metropolis algorithm, the basic step was a spin flip in the X, Y, or Z direction.
Right.
But that does not create entanglement, right?
No.
So how can you then use this to sample a state which can have entanglement?
It's the next step. So, so where you apply it's basically these terms exponential of IH, right? Exponential of IH is acting on the entire system and is creating entanglement on your space.
Ah, okay. Okay, thanks.
Thank you for the nice presentation. So coming from the condensed matter community, we always think about the spin coupled to bath that leads to the Kondo effect. Can this Lindbladian approach capture that?
Sorry, can it capture?
The Kondo effect, in which the environment responds to a spin flip, and then another spin flip occurs, and the environment kind of didn't finish to respond. So there are correlation between the reaction of the environment to spin flips.
Yeah. It's not my speciality, but I thought the Kondo effect was a zero temperature effect.
No.
You took the temperature, no? Okay.
It was measured in experiment, so it's certainly at finite temperature. And it seems to me that somehow this Lindbladian formalism misses this point. So if you can,
is it a Markovian effect? Do we know this?
It's just correlation between when you have a spin flip, the environment responds to this spin flip, and then before it finishes to respond, there is another spin flip. So there are correlation in the environment.
It's non-perturbative. So I think it's non-Markovian. So I think it's not in the. So the assumptions we make in the derivation, I think, probably exclude the Kondo effect. That's my guess.
More questions? There's one in the back.
Yeah. Hi, Michael. Fantastic talk and amazing results. I actually have a meta question because you tell a very cautionary tale of an old result that was wrong and kind of like fully believed by the community, which hampered progress for 15 years, more or less, right? Is there any advice you went through this that you could maybe give us that these things happen less frequently or that we become more aware of them?
Yeah, I think first, wrong and right is not as binary as it sounds. So a lot of the insight from the original paper was extremely useful in further developments. And when it came to commuting systems, it didn't really matter that much. You know, one has to remember also the community was much smaller back then, right? So there wasn't as much checking. I don't think there's much, you know, these things happen. There was no cheating involved. It was, the 2010 paper was a fantastic result. In many ways, it was a result which was ahead of its time, right? So maybe the community just needed the extra tools to really get past the hurdles that were available.
Thank you. Let's wrap it up here. Thanks for Michael again. And then, as I announced earlier, let's use the final few minutes for this award ceremony, this poster award ceremony. So last night we had the poster session for the Spin Qubits workshop, and then 3 of the posters were selected by an esteemed, distinguished expert committee who was exploring all the posters and scoring them. And maybe with the help of Szabolcs, I would like to now hand over the prizes. So there are three prizes. Yes. So I start with the 3rd prize. So this is actually coming with some money as well, so 200 euros, thanks to our sponsors. And this is going to Anirban Das, who works at the Budapest University of Technology and Economics. His poster title is Hexagonal Germanium Nanowires as a Spin Qubit Platform. So Anirban, if you're around, yes, please. Congratulations. But the money is over there. Congratulations. So the 2nd prize goes to Gulibuzitan Abulizi from the company C12 Quantum Electronics for the poster Microsecond-lived quantum states in a carbon-based circuit driven by cavity photons. Congratulations. Congratulations. Thanks. And finally, the 1st prize, which comes with 500 euros, is for Edmondo Valvo from Delft University of Technology for engineering against disorder, mitigating G-tensor variability in noisy germanium, silicon germanium Hall qubits. Congratulations. Thank you. And congratulations once again for all the recipients.